Today we are going to do section 3.5, which is called Other Strategies for Integration, which just means we're going to repeat what we've been doing already, okay? What other strategies are there? First, use a table, which we have already done somewhat. And second, use the integrator, okay? The definite or integral calculator, I mean. They call it the CAS. We're not going to call it that, okay? We're just going to call it the integral calculator. So let's look at this, right? If first, the book mentions that if you do the integral of, say, some standard problem, you might come up with two different solutions right here. See, you have the integral of the, and one is called natural log of something, the other one is called sine h, inverse of something. You think, well, why are there two things? Well, the reason is because the sine h is a function that doesn't deserve to exist, okay? We should just go by the natural log. Forget the hyperbolic functions. They're a waste of time. And because they cause this kind of situation. See, I mean, you have two functions when they are actually the same. If they're the same, why do we have another name for it? It's a waste, complete waste. So basically the hyperbolic functions are complete waste, and I'll show you more of why that is the case later. So let's look at example 3.36. We are doing this by some kind of a table, and we have done, well, it doesn't matter, we've done it. Okay, so that is just a standard problem, I believe. And so please do that problem as your homework. Now in example 3.36, they use a trick here, okay? To do the integral, what they did is they multiply the e to the power x. See here? If they multiply e to the power x to both the numerator and the denominator for no reason. Now in our previous homework, we did exact same thing for a reason. The reason, however, is so that we can provide du, which becomes ex dx, and then everything will work out properly. So once you've done that, you dig out the formula from the table. In this case, it's offered to you, right? It's already written down, and you plug it in, and the answer pops out very nicely. So that's that. Next, the book describes how to, example 3.37, which the book describes how to use the online integral calculator. Well, that you just type it in. There is not much to that, except that sometimes when you do that, you might come up with some weird junk. Other times, you might come up something that looks decent. Now, in this case, something decent did show up, so please do example 3.37 as well, because that's a decent answer, and we can always use a decent answer. So that you just type it in and stare at the answer. That's all. Now, in example 3.37, I should mention that in natural log situations, sometimes remember that when in natural log, when you have the log of a divided by b, that translates into subtraction, right? Like in this case, look at the bottom here, this long line, where you have natural log of that stuff, everything's over 2. 2 is in the denominator. That's the same as subtraction, okay? It's the same as subtracting natural log of 2, and that can be ignored because that's just part of the constant in the indefinite integral. So that's why sometimes it might be missing a division or multiplication by some kind of a constant. But otherwise, it should be identical. So that's that. So next, let's look at the example 3.38. Example 3.38, again, we are going to type in the answer for a very standard problem, the integral of sine cubed of x. Now, if you do that, then you realize that the calculator come up with something that looks distinctly different from, see? The calculator came out with something that looks distinctly different from the actual answer if we were to just follow the table. There is a table for sine cubed sine cubed of x is integral of sine cubed of x is in the table, which is in Appendix A on page 700. I remember it because it's just 700, right? So if you look in there, you will find the answer. But if you type it into the calculator, and especially the book, the Wolfram calculator, it tells you some number that has a whole bunch of multiple angles in it. That is, they gave the answer as cosine 3x instead of the right answer, which is a little bit lower on this side right here. Well, that's nothing. I mean, I remember one of our previous homework problems where the answer was huge and with all kinds of the multiple angles. It was ridiculous. It didn't. Well, the reason is because those two are trig identities, okay? And if you work on it hard enough, like this, if you want to practice your trig identity, you can do that. The stuff on the bottom where you prove the one is actually the same as the other. But for me, I recommend that you skip it. And we're not doing trig identities right now. So let's skip this example, and that's it. That's the end of this section. And well, that's because this section didn't tell us something that we haven't already done, right? But it does summarize all the stuff that we have noticed all the way here in chapter 3. So it's still good. So we are going to do some homework here. For chapter 3, the homework on page 314 is please do that section 3.5 homework. Is please do problems 245, 47, 49, 51, 53, 57, 59, 61, 67, 71, 84, 85, and 87. And when you're done with it, I want to talk about it. Now, but before you do the homework, I want to remind you that for all the homework assigned here, sometimes they tell you to use the calculator and sometimes they tell you to use the table. Either way, I want you to use the table or some of the means for every single problem. That is, do not trust the calculator. Okay, the integral calculators are pretty good, but they can go crazy, and you gotta watch them like a hawk. Right? I mean, remember this problem, okay, in the previous section, problem 163. Remember this thing? Okay, I mean, what does the Wolfram calculator say? It gives us the answer to this, which the symbol lab it came out with the same answer I did. See, the answer is simply the arcsine of 1/5 x over 5 minus 1, piece of cake. But the Wolfram calculator came out with this thing, which is unacceptable on many levels. And one reason it's unacceptable, as you notice, they have the tangent h in there, the hyperbolic function. They should not have allowed tangent h even in the program. I mean, that's probably what screwed it up, like this. Well, I don't know if that's what screwed it up, but that would be my guess. And but it does makes me laugh. It's great fun to watch the calculator screw up, right? I mean, I've never seen a calculator screw up before this. All the calculators we've had, the regular calculator, then the scientific calculator, then the graphing calculator, I've never seen them make a mistake before. This is now we got to the integral calculator, and now they're screwing up. How neat. Anyway, so when you do your homework, you can use the calculator, but do not trust the answer in there, especially if the answer, number 1, is huge, and number 2, doesn't look like the answer in the back of the book. Now, the back of the book answers sometimes are good. Sometimes they just copy and paste the calculator's answer, which turns out to be completely off, okay, as that example I just showed you did. Because the book also showed, for that particular problem, the book also showed a similar answer to what the calculator said, rather than a simple answer that we came up with in 2 different ways. All right. So anyway, so please do your homework and be sure to do every problem without the calculator. And then you can use the calculator if you want. And when you get back, I will talk about the problems. Now that you're done with your homework, let's talk about it. Problem 245, which is identical or similar to example 3.34 on page 305, which I have written down. And take a look at my notes. I'm waiting for this thing to focus. There it is. So the problem 345 is a partial fraction situation. So you follow the partial fraction rules. But in this case, this thing doesn't break up, okay? And because it's got no roots. So then, no real roots. So then you have to do that trick called completing the square, which will get you beat it around until it looks like some kind of a square situation on this side. See the square here. And then once you're in that form, you will, next step is let u equals to x plus 1. That will get you into a u situation like like this. And then you will follow rule 16, which I wrote down on the over here. And then you just plug it in like it says, rule 16 for well, for one part of it. The other part you just do basic what is the other part? Oh, the other part is just substitution or something. U substitution, where you let u du this part you just, because the derivative of the bottom is just the top. See, there's u squared down here and u on top, so that conveniently turned into a natural log situation. And the other one, of course, becomes the tangent inverse, and that is your answer, and that's correct. Oh yeah, I forgot. Don't forget to put the u back. What was u again? U was x plus 1, so plug that back in. And in fact, u was the original thing up here, the part of the original problem, x squared plus 2x plus 2. And anyway, so you plug it all in and you got the right answer. Next, let's look at problem 247, where we have a situation here with the square root of a bunch of stuff. So the trick is that let's do the completing the squares thing again, where to be able to use the table. The problem says use the table to solve this. Well, first we got to make it look like the table somehow. To make it look like a table, we'll do completing the square, which is and take a look at my notes. We see to complete the square, we plus 6. Well, you complete it somehow, okay? And then and by doing taking the 6 divided by 2 and square it, and then subtract it out to be fair. And then what we have is a situation that looks like this, where you let u equal to x plus 3, then it becomes rule 81. If you look at the appendix, which is on page 700 or so, plus 8 if you're scrolling on your computer. Okay, the computer page is different from the book's original page by adding 8 to it. So so once you get that, look at rule 81. That tells you exactly what it's supposed to be, and you plug it right back in, and there's your answer. Okay, you don't even have to write down u, just put u back in what it was. Am I missing something here? Yeah, I'm missing a line. Let me draw the line in. So I was missing a line, see, for the natural log up here. Not a big deal. I mean, on this side. Yeah, now it should be good. So that one, if you check so that one is correct, or should be. Now, if you look at the answer at the back of the book, it will give you a completely different looking answer involving the hyperbolic functions. The reason for that is because the inverse of the integral of hyperbolic functions does look that way. Okay, here's a chart that I got from Calculus 1. Now look at the cosh function, that like the answer at the back of the book. See, the cosh function, when you take the derivative, is 1 over square root of x squared minus 1, which you can be adjusted, and then it'll turn out to be the answer in the back of the book. However, you also notice that if we are supposed to do this problem by looking at the table, and there is no table that involves that integral that I just showed you. Okay, you know why? Because the guy who built the table also thinks the hyperbolic functions are a giant waste of time. So he did not include it, and as a result, that answer theoretically should not be acceptable for this problem. The answer I showed you is the right answer. Okay, because that came from the table at the back of the book, like we're supposed to, right? So so that's that. Now next, problem 249. Next, let's look at problem 249, where it says that we're supposed to integrate this thing that's very, very convenient. Now, remember, well, in Appendix B, that's a couple pages after page 700, we have the rule here, just to remind you, where the derivative of something like b to the power x is this thing. Okay, it's just b to the x, except that you have to multiply natural log of b there as an adjustment. So then to integrate this thing, see, everything comes out nicely. So you figure out what the integral of 2 to the, is this clear enough? Maybe like that. Okay, 2 to the, it's very bright. Why is it so bright? Well, anyway, I will figure out why it's so bright later. Anyway, so you figure out the derivative of this thing is, and then the integral is just something like this, maybe divided by the extra 2 and the extra natural log and that kind of thing. No, there's no need to worry about natural log of b, I guess. What? Where's natural log of b? Let me look at this. Well, never mind. B does equal to 2. That's why I have natural log of 2 there, because B is 2 in this case. So then the answer comes out nicely, and that is the same as the back of the book. Next, let's look at problems 251 and 253. They are both one-step solutions when you apply the appropriate integral rules. So I won't talk about them too much. So I just let you take a look, and you can stop the video there and look at it in detail. So next. Same thing for 257. 257 is a one-step integration because there's a rule that explains that directly gives you the solves the problem of integration. Rule 20 will fix 257. You have to you do the evaluation in this case, which is fine. Go ahead and do the evaluation, and that the answer will pop out right away. Next, problem 259, where again we have a direct rule to apply for that sort of thing, tangent to the fifth power, and that's rule number 30. If you have tangent to nth power, there's a reduction rule to crank it out for you. So then we apply the rule, okay, and the rule 30 on page 700 or so, in Appendix A. We apply the rule, and then we end up with something like this, okay? So we have knocked it down from the fifth power to the third power. So we need to, at that point, we don't have to reapply the rule. We could, but instead, we can just go to rule 24, which is just the exact integral of tangent third power. That way, we don't have to work too hard. So when you plug that in, taking care of various multiples, because remember, the rule 24 only applied to the integral right here, and that integral is being multiplied by 1/3 earlier. So you got to watch out for that and take care of that. So once you take care of all the integrals, then you plug everything in, make all the numbers come out, and you'll come up with the right answer. The only difference is you notice that at the end, I have the answer cosine 3x, which with a minus in front, whereas the book, the answer has secant squared with 1/3 in front, positive 1/3. The reason is because the natural log, when you have the power, is the same as subtraction becomes the power. Okay, so you can put a negative sign on top of cosine, and that becomes the secant. Like yeah. So that's that. See? Negative natural log of x is natural log of 1 over x. So next, let's look at 261, where you have the integral of 1 plus secant w over 2. And this problem, you are supposed to do it with the integral calculator. But if you did, you're going to end up with something that looks distinctly different from the answer provided in the back. So we're going to just go ahead and find the answer provided in the back and ignore whatever it is the calculator said. What the calculator said doesn't look terrible, but it doesn't look like the answer in the back. So we're going to get the right answer, which is the one in the back. Even I think the author probably intended for you to do the problem following the answer. Following the calculator. But when he went to do the answers, he forgot that he was supposed to do that, so he just did it the normal way. And here's the normal way to solve 261. What you're gonna do is that one plus secant thing. Where is it? And let me move it a little bit. There we go. Okay, my camera is having a hard time focusing. Why? It's still not focusing. Come on. Okay, there it is. Now to do this thing, what you're going to do is you pull a trigonometric trick. That is, you're going to multiply down here 1 over 1 plus secant x by 1 minus 1 plus secant x, both top and bottom. And then you beat around the trigonometric identities and stuff and end up with this thing down here, right here, okay, which is cotangent x cosecant x. I don't know if you can read it. But that says cotangent x cosecant x plus 1 minus cosecant squared. And when you do that, then and that makes it easy to integrate because all those things are readily integrable. Okay, cotangent cosecant comes from cosecant. Okay, and then cosecant squared comes from cotangent. So then the answer falls right out when you substitute the w over 2 back in and take care of that 2 there. So you have to, which means you have to multiply by 2, but the answer does come out nice and neat. See down there. Yeah, it's pretty good. And that's the answer of this problem. And so the problem basically just you just have to try to figure out the right trick identity to reduce this thing to something that's manageable. And so let's ignore the fact that the calculator gives a different answer and move on. Next, 267. What do we do there? Is the integral of x cubed sine x. Now, how do you do that? Now, you might remember that the normal way of us solving this kind of problem is by something called integration by parts. So I went ahead and did that. See, being integration by parts, we followed that Liat principle where in the list as algebraic expressions goes before trigonometric. So I let u equal to x cubed, okay, etc. And I came out with something like this. So I ended up with x cubed and then the integral of x squared cosine. So I'm down 1, okay. And by then I was worn out. So I decided to do something else. So I look on the appendix A on page 300 or so, rule 39, which if you look at rule 39 is a reduction formula that makes things much better. So then I followed rule 39 on page 700 plus 8, which says that and set n equal to 3, and I got this. So then I get right here, okay, which is similar to what we got before, okay, almost identical. It equals to this, and then well, actually, that's identical to what I did before, so it didn't do me a whole lot of good. However, then I proceeded to use rule 40, and I proceeded to use rule 40, where we have that is just for x, the exact thing. Okay, by rule 40, everything is it's just x squared, right? So you plug everything in exactly, and then we have one more, which I use rule 37, which is just sine x minus cosine x, I guess. And then I think I wrote it all out to make sure that everything's right. And being that we are supposed to use the calculator, I plugged this thing in the calculator as well, the x cubed sine x integral, and that came out to be identical. So the calculator did get it right this time. Lucky for it, okay? But we want to do it ourselves to make sure the calculator isn't going nuts. You never know when that thing might go nuts on you. All right, so that's that. Next, let's do 271, where we have the integral, a fairly short and straightforward answer. We have what we're gonna do is the u substitution, where you let u equal to x minus 1, and then of course x becomes u plus 1, and then you plug it all in there, and then what is that? And then you end up with something that's still somewhat puzzling looking. So you do it again. You let v equals the square root of u. Now at this point, you notice that when dv takes care of the square root of u in the denominator. See, it works out, it lucked out, basically, is what happened. So then the whole thing turns into 2 over v squared plus 1, 2 dv over dv squared plus 1, and that is the tangent inverse. I forgot to write down which rule that is, but that is a standard one, okay? The 1 over x squared plus 1, the inverse, and you can look up the rule. It's one of the earlier rules. And then that comes out to be, you plug u back in and all v back in, then u back in, or something like that, and then come out with this answer. which is the same as the back of the book and what the calculator says if you plug the problem into the calculator. Next, let's look at problem 284 and 285. Now, 284 looks kind of hard. You got natural log, then you got sine inverse of the natural log, etc. Until you realize that if you let u equal to natural log of x, everything will fall out beautifully. So let me show you what I mean by that. It's like a two-line problem, right? 284. You let u equal to natural log of x up here. Then, x is bigger than 0. That's maybe x is bigger than 0. I don't know. I don't know if that really matters. But anyway, we'll take the derivative and then we get u sine inverse of u. And how are you supposed to do that? Well, as it turns out, there's a rule 62, that directly takes care of that. So let's plug all that in like it says, and then plug in u. What was u again? Plug that in, and then you get this big, long, impressive looking thing that is we don't have back answer at the back of the book for this even problem, but the calculator says the same thing, okay, when I plugged it in. So it must be right. So that's that. Next, let's look at problem 285. That one is a direct application of Rule 72, so I skipped it. Next, let's look at problem 287, which is a derivative of a trigonometric situation. And how are you supposed to do that? Well, at the end of the day, you end up beating around some trigonometric identities and get it to come out looking better than what it does. So look at all the various trigonometric identities I used. When you beat it around on this right side here, you notice that it end up being the whole function end up being 1 over sine squared. Okay, and taking care of the coefficients, I mean the numbers. Okay, there's a 1/2 here that don't forget it. So once you've done that, however, the 1 over sine squared is just secant squared. And then by rule 8, the derivative of cotangent is cosecant squared with a negative. Okay, so not forgetting the negative sign, you plug it all in, there's your answer. And that is the same as the back of the book. 287 is the last problem, so that's it.